For this project, we performed an experiment relating many concepts seen in class. We are first going to explain the basic theory needed to understand the topic. Then, footage of the experimental procedure will be shown. And lastly, we'll discuss our findings.
We're going to talk about the X-ray particle duality behavior. We have this experiment in which we deal with X-ray production, then a diffraction pattern governed by Brag's law, and we're going to focus on the analytical side and the experimental side of the detection of these diffraction patterns. So first, let's think about the first step in the process, which is X-ray production. Well, basically, X-ray production is explained by this circuit, which has a potential of the order of magnitude, which is kilovolts. Here we're analyzing a 40 kilovolt circuit. And the interesting phenomena occurs at the cathode and anode. So we have electrons arriving at the cathode, and here we position a heater which expels the electrons. And these expelled electrons have precisely 40 electron volts of energy. And that acceleration changes when they arrive at the anode. Let's suppose the electrons lose all of their kinetic energy. So we use Planck's law. Then solve for frequency, and we get something around the order of magnitude of 10 to the 18th, which translates to a wavelength of about 3.2 angstroms, which is in the order of magnitude of 10 to the minus 10 meters, and in the order of magnitude at the same time of the size of an atom. So let's make a zoom on the circuit we had previously. Here, the electrons that flow from the cathode to the anode strike the anode, but let's be specific on what's happening in the anode. The anode is made up of copper or sometimes tungsten atoms. So when the electrons collide with these kind of atoms, it produces a characteristic radiation, which is in the order of X-rays. And we know the lambdas, which are characteristic of these atoms. So by knowing the lambdas and the striking angle on the sample, we can know the inner structure of crystalline solids with the help of Brag's law.
We now are going to talk about the real procedure, the real experiment in the lab. So before we get into that, first we have to explain how exactly the machine works. So the machine consists of three main parts, which is the X-ray producer, the sample, and the detector. The X-ray producer works just as our classmate said. Inside we have a filament, a plate, and the whole process will make X-rays. So these X-rays will cover this path. They will come through here, which acts as slits, just as to canalize the laser and to make it stay in a single path. So then the laser is going to strike the sample and it's going to bounce. The angle is marked here, but the actual machine measures 2 times that angle, and that is important in the next calculations. We have to take into account this factor of 2. So the laser comes here, it bounces back, and it falls in the detector. This will rotate with the detector, so the sample will make this movement, and the ray will be continuous. So what the machine is getting is lectures on the intensity. The X-ray we used in this case was a copper one, and each X-ray has 2 characteristic wavelengths. One is alpha and one is beta. In this case, we don't care about beta, we care about alpha. So the alpha wavelength on X-ray with copper cathode will be of 0.1541 nanometers.
So we have this triangle and we have the distance between planes. We know that the X-ray photons are emitted at a certain angle, and with respect to the crystal, so we try to get this distance. We know that it has to travel this distance, but also this distance. Also, it should be the same. So it should be 2 times d sine of theta. And this should be equal to the wavelength multiplied by an integer.
We're going to talk about how to analyze the data, or what type of data are we obtaining from the experiment. First one, we said that the machine detects the rays as they go through the sample and bounce back to the detector. So what we are getting is completely in relationship with Bragg's law. That means every time the diffracted ray accomplishes Bragg's law, we have a maximum because we have a constructive interference. So the graph of intensity versus time that conveniently the software made for us will look like this. It will be the time, and each time we arrive at an angle which this is accomplished, we will have a peak, and the data will produce like this. I will produce peaks. After movement from 0 to 90 degrees, the experiment stops, and we have to analyze these peaks to associate a certain group of Miller indices to each peak. And this process of the Miller indices will be explained later in the video.
Miller indices are used to calculate the planar density of a certain unit cell. So for instance, say we want to divide our unit cell according to this one, this way. Now you want to be half to the length of the unit cell, and you want it to be straight on the y-axis and on the z-axis.
New value, yeah.
So what this tells us is that x only can take one value, and y and z can take all the values. To calculate, for instance, the density plane of the top of the roof of the unit cell, you're gonna have on x, as you see, you're gonna have infinity, and on y you're gonna have infinity, and on z you're gonna have 1. So we take the reciprocal and we get 0, 0, and 1. This is on the simple cubic unit cell. This has the highest density. And it agrees with our results, stating that this density, this plane has the highest density, so it has the highest intensity of photons reflected. So in the experiment, we have the crystal and the emitter of X-rays, and they are both rotating, so that we can see all the angles, and thus we can get the density, that the plane density that is the highest for each crystal. So we can identify then the type of unit cell according to the intensity and the angle that is emitted.
Just as it was previously explained, inside the X-ray diffractor there was a tungsten filament which was heated in order for it to shoot electrons into a copper plate. This is in essence the photoelectric effect. We then inserted a small film with a potassium chloride sample and used 40 kilovolts and 50 milliamperes through a process called aging. With help of the software Miniflex, we obtained the following interference graph after some time, from a range of 5 degrees to 80 degrees, clearly showing us the angles at which the most photons were received by the detector. With the peaks we obtained from the experiment, we produced this table, allowing us to calculate the cell parameter of the crystalline structure using Bragg's law. Our data shows that this result remains constant, which was expected since the parameter is a physical characteristic specific to the compound being analyzed. When we took out the sample from the XRD, the potassium chloride was pink or lilac. This coloration of the sample is known as an F-center or a color center formation. This phenomenon is characteristic of alkali halide crystals, such as our sample, and it is a defect formed by an anionic vacancy in the crystalline structure, which interestingly enough is formed by mainly due to Compton scattering. In this case, the inelastic interactions of high energy photons with the electrons in the sample cause them to recoil, and for some semiconductors and insulators who have a large enough band gap, such as this salt, the electrons can be ejected and become trapped in the place of the anions. This results in a modification of the range of wavelengths the material usually absorbs, leading to a macroscopic color change of the sample.